Tonight on Revolutionaries.
Our tagline is Smarter Planet, but it's all about information technology moving out into other problems, that the world was becoming our lab.
In nearly a century of innovation, the research labs of IBM have produced breakthroughs in everything from microchips to the Jeopardy-playing supercomputer, Watson. Dr. John Kelly, who directs all global research for the company, talked with us about the ambitious agenda he's pursuing. Major funding for Revolutionaries is provided by the Intel Corporation.
We're so glad to have you here tonight, John. And you and I have actually had a pretty fun afternoon because we celebrated the arrival of Watson and the Jeopardy set here at the museum.
That's right. So big news.
I think we have a picture, actually, of the way that this looks, if you want to bring that up. So there it is. That's the actual set that was used for Watson to play Jeopardy on television. It's now in our graphics theater as part of the Revolution exhibit. It's just terrific that you've made this possible. Thank you.
We're privileged to do it. We have a great partnership with the museum here. And as you said, it's only fitting that Watson is now amongst its genetic relatives, if you will, here at the museum. You know, I was asked downstairs, John, is that a replica of the original stage where Ken Jennings and Brad Rutter competed with Watson? It is not. It is the original stage. In fact, if you look at the buttons, you can see that Ken Jennings wore the paint off the button. He was trying so hard to beat Watson.
I noticed that literally the paint is missing at the bottom of the buzzer.
Right. That's right. And if you watch the game itself, towards the end, as he realized he was up against some pretty tough competition, I thought at one point he was going to throw the buzzer, but he contained himself.
Yeah. Well, and the dollar figures sort of tell the story, don't they? I mean, Watson wins going away.
Yes. And, you know, I should say that just a short story. Going into it, I remember I had the privilege of speaking with the audience before the game actually began. And I remember saying that we might witness something amazing tonight. That I felt that we were at a point in computer technology where in open domain questioning in natural language that a computer could compete with and perhaps win against two incredible human beings in Rutter and Jennings. And I remember saying that it was not a question of if, it was only a question of when. And that if we did not win that night, I was sure within a year that Watson or another system would be capable of beating him. And of course we went on to win by a substantial margin, thanks to some double jeopardies and some other things.
Now, you were telling me an amazing thing, which I don't think I knew, which is that part of the conditions under which the match occurred was that IBM had to build a mechanical finger to actually ring in, just like the other human contestants had to ring in.
That's right. That's right. After we had reached all the agreements with Sony Entertainment that owns the show itself, and we had sort of set up the rules, they said, oh, by the way, one more thing. The humans have to buzz in with a button, so Watson has to have a button. And we said, well, Watson has no fingers to push the button. And they said, well, build a finger. Now, building a fast finger with a fast button is a challenge that we were up to. And we built probably what is the fastest finger. But it was fast. But again, it wasn't just obviously the speed of the button. Watson had to know the answers, and more importantly, it had to know when it was fairly confident, and it had to know when it didn't know. And I think it's probably, again, sort of the first time that a system was aware of itself and what it knew and didn't know, and also was aware of its environment. It was aware of what its competitors were doing and what they were capable of. So, but we'll get more into that.
Sure. So let's talk for just a bit about you and how you decided to choose IBM. I mentioned earlier that you joined IBM right out of graduate school. What were the the thoughts in your mind at that point when you decided to do that?
That's a good question. We did not rehearse this one. It was actually quite simple. I had interviewed with a number of different companies, including some of the companies in the room today, and this evening. And the interview, there were 2 points in the interview at IBM that completely convinced me this was where I was going to work. First, entering the plant in Poughkeepsie, New York. You enter through what at the time was the manufacturing and test floor for our largest systems. And you walk through an acre of large systems with the backs off of them, test equipment, engineers on them. And not only that, but the name of the customer was over the system. So you would see, Sears, all of the banks, et cetera. And so I saw world-class technology, enormous scale, tied to customers, solving problems.
And Poughkeepsie really was the mothership at that point.
That was the mothership and still is the mothership for large systems. And at that point, it got my attention. I'd say the next point was I had gone through all the usual interviews and wasn't convinced that that was where I wanted to work. And the last manager I interviewed with, he was very intuitive. He said, "John, I know we haven't convinced you to be interested in IBM." So he says, "Let me really show you what we're working on." Now, this was 1980. Opens his drawer and pulls out an electronic module, about 5 inches on edge. And it was a thermal conduction module with 100 chips, multi-chip modules, 70 some odd layers of ceramic. And he said, "This is the brain of the new IBM systems. And this is why we need you to come here." It wasn't working at the time.
That's why it was in the bottom drawer.
But I looked at that piece of technology, and I had been around enough other companies, and that was decades ahead of any other company or university that I had looked at. And I decided at that point, this is where I'm going to work.
Why research? Research is not always the place to be inside a technology company. It certainly has been at IBM. Right. What was it about research in particular at IBM that made you turn in that direction?
Yeah, our company, I think, John, is very unique in that we understand who we are, and we understand why we survived 100 years and prospered 100 years when many other companies passed. And it's that the IBM corporate strategy, culture, values is all around innovation. I think, many people, companies use the term, but we put our money and our best people where our mouth is. $6 billion a year in R&D.
$6 billion.
$6 billion a year in R&D. So it's part of our strategy. We fundamentally believe that in the information technology business, there are only 2 ways to succeed. One is an innovation approach, and if you're going to do that, you better invest to innovate, and you better hire the smartest people in the world, or you better be the lowest cost commodity supplier on the planet. Any place in between is metastable. And so we have chosen over 102 years now the top approach, innovation, constantly understanding that technology, its time will come and pass, it will commoditize, and we need to constantly innovate and move up the value chain.
When you first got involved with it at the management level, when you first moved into IBM Research and really had your hands on the levers, what was the approach at that point, and how would you say it's changed over the period during which you've been in charge?
Well, again, IBM Research is approximately 60 years old in the company. Our roots go back to Columbia University, a Watson scientific lab. And out of that grew IBM Research.
So it was university-based from the beginning.
University-based. And if you look at the evolution of IBM Research, I would say that, as you mentioned, we have 12 labs around the world. The first group of labs were very much labs that were established in or around the great universities of the world. So, obviously, Columbia University, our Yorktown Heights lab, our Ahmed, California lab near Stanford and the great universities out here, Tokyo Research near Tokyo University. So first phase IBM Research labs globally were co-located with great universities or close by. So I sort of characterize that phase as, the lab and the university is our lab. We needed to get near the smart people. What's changed in the last decade or so that I've been leading IBM Research is we realized that we still need to do that, but as the world in IT has changed and moved out into the real world, our tagline is Smarter Planet, but it's all about information technology moving out into other problems, that the world was becoming our lab. And so our laboratories then moved out sort of in a second phase into high growth markets in India and China, places like that where the sorts of information technology challenges were completely different. An information technology problem in a large telecom in India is a lot different than something that we're doing in the United States. And then the third wave, which really represents our last 3 labs that we've opened in the past 2 years, in South America, in Brazil, in Australia, in Melbourne, and most recently in Africa, in Kenya. We're going now where our clients and where the problems are. So there's the only way to really understand and do research on information technology in natural resources is to be where the big natural resource companies and clients are. And so we move to places like Sao Paulo and Rio, where the big oil companies are doing research in pre-salt oil on the big oil discoveries off of South America. So we really have not only changed the kind of work we've been doing, we've been changing the locations, and I think it's a bit of a reflection on the IBM company that we change so rapidly. And I think in our industry in particular, it's necessary, or else you don't become an active participant in your museum. You become a relic.
You become in the back.
In the back.
So that's such an interesting evolution because you started with a university focus.
Yes.
And then you said the last 3 have been more client focused. What does that say about the nature of the university relationship to research and development now versus a more privately driven model in R&D? Is that, can you generalize about that, or is that something that just happens to be unique to you?
I believe that this partnership between industry, academia, and in many cases governments, that collaboration is really the secret sauce to doing world-class research and having impact with the research that you're doing. It's become the model. If I go around the world, we have a lab in Dublin, Ireland. It's a collaboration with the university there. It's a collaboration with the city of Dublin around smarter cities. The city of Dublin gives us access to all of the real-time city control information. It's a gold mine of information. In order to create that lab on my own, I'd have to go build a city. Whereas here I partner with the government and the city of Dublin to get access to that, and I bring in the best faculty from the universities. Same is true in Africa. We're at the Catholic University of East Africa. We're co-resident on the campus with some of the best minds in Africa, in Kenya, working on African problems in healthcare, in resources, in simple things like water supply, power supplies, which are a great challenge, traffic, et cetera. So I think it's this partnership is a very, very important model for research if you want to have impact with what you're doing.
So I'm going to talk a bit about some specific stories. And I heard you speak 2 years ago in New York where this amazingly fascinating story was told by an executive of the Mars Corporation. Now, for everyone who doesn't know Mars, Mars is the Mars of M&M Mars.
Chocolate.
Chocolate. Something very important to society. Let me just make that clear. The story that I'm telling you is vital because of the existence of chocolate. And I remember he had this wonderful opening line. He said the 2 most secretive organizations in the country are both based in McLean, Virginia. The second most secretive is the CIA. And the first most secretive is Mars Corporation.
Right.
But Mars Corporation came to you because they had a desperately bad problem, which is
Yes.
the death of the cocoa supply,
That's right.
much of which they either cultivate or own directly. And cocoa trees, as he told it, were dying by the hundreds, and they had absolutely no idea what was causing it and no way of stopping the eventual eradication of cocoa, which would be a disaster.
Right.
So can you pick the story up from there and how you came into that?
Yeah, so they came to us, and we do this quite often with clients. We'll say, well, what's your biggest problem? And in this case, we weren't prepared for what they were about to say. They said, our whole corporation, the majority of our corporation is built on the cocoa supply. And we lose about 1/3 of our supply every year. And not only is that impacting, due to various bugs, fungus, et cetera, they said not only is that a problem for our corporation, but by the way, there's a billion or so people whose livelihoods depend on growing cocoa in places like Africa and South America. And we have the best laboratories in the world, and we're doing all of the wet chemistry and biology to try to solve this problem one at a time. But they knew that we had been working on the human genome. They knew that we had built the blue gene supercomputing systems to help decipher and crack the human genome. And they said, you guys probably wouldn't be interested in this, but our biggest problem is if we ever could map the cocoa genome, we could open up whole new branches of herbicides and other things. And being IBM Research, the bigger the problem, the better. Can you build a machine to beat humans at Jeopardy? Can you crack the cocoa genome? And a couple of our researchers just said yes. Then they came back and told me.
What do you do when someone walks in and says, oh, by the way, John, we've decided to map the cocoa genome?
Yeah. Well, we go and do it. Do you have enough resources? Blah, blah, blah. So we did it, and we did it in a very short period of time. We have obviously immense computational power, but in addition to that, what is really key is that we have actually biologists and genomists on our staff. So one of the unique things about IBM Research is not just a bunch of computer scientists or physicists running around. We have medical doctors, we have biologists, we have astronomers, we have people from all fields. And so they went to work on this problem working closely with Mars. Mars taught us everything they knew at the time about the genome, and we cracked it. And the interesting thing, and I think it speaks so much about the Mars Corporation, is that they basically then wanted to open source or make open the genome so that it could now be worked on in multiple areas.
Right.
And so some very specific genes have been identified out of that, and whole new ways of preventing the loss of the crop has come about. So I think again, it shows, the world and the client is our lab. We wouldn't have even have thought about doing that. Now for IBM, that was, a nice demonstration of capability, but as you might imagine, people in other food supply chains and other areas of biology immediately came to us and said, well, if you can do that, how about cracking this one? And so it gives us a constant pipeline of challenges.
Did you learn something from that you hadn't known about genomics? You said you've been working in the human space for a while, but what lessons, if any, did your team take away from working on cocoa?
Yeah, I think it's what we learned and what we continue to learn, John, is that there's nothing like working with clients. And the one thing IBM has is client relationships that go really deep, not just at the science level, but through the whole corporation. And it really takes, they didn't just do a data dump on us and then we crunched it on a big computer. Their best top researchers and mine work side by side to do this. And the knowledge flow when they do that is incredible. So what we really walked away from that with was we have to partner deeply with clients, whether it's with the Mars Corporation or a bank or a retailer or a medical institution, close relationships. And I would definitely say, John, that influenced how we thought about what next for Watson. We knew it wasn't about game shows. We had some ideas what to do, but it influenced our thinking in terms of we better have some big, strong, knowledgeable, deep partners to take Watson to the next level.
So let's talk now about that. This is a good time to pivot to that
Sure.
whole area, which is this emerging flavor of computer science that you have called cognitive computing. And we joked as we were getting ready for this evening that you're in one of the few places in the country where you could talk about the death of the von Neumann architecture,
Right.
and people would actually know what you were
That's
talking
right.
about.
I feel at home.
But not everybody will know about what is fundamentally changing about the way we've always thought about computing up to now, and the way Watson and this new model of computing is beginning to change all that. So let's start at the beginning. Talk about the architecture that all of us have always known, whether it's big computers that you're talking about or the laptop we have on our desks, and how that is not sustainable, breaking down, or new forms of computing are actually starting to take hold.
Sure. Well, I would sort of start almost then with prehistory, which is what I would call the first era of computing, which is a tabulating era, and you've got some great examples here in the museum of Hollerith machines and others, and they were mechanical devices that basically could do addition, subtraction, some very simple tasks. But the next era of computing I refer to as programmable, which is everything that we all know today and our whole careers have been based in. And these are systems that fundamentally are von Neumann architectures where you store a piece of information, you use a processor of some kind to do a calculation, and you're moving data, calculating, et cetera. And the way you control that is through what we call programming. We tell the system, in exotic ways, do this, move this bit, do this calculation. And then we stack that up through different ways in software and build applications that, fundamentally do what humans do, but do it much faster. That has been good, and we've taken it, through 60 some odd years, and we've achieved tremendous goals with that. But fundamentally, we had to program the blue genes that did that calculation that broke the cocoa genome. And everything we do today to our cell phones are programmable systems. We realized a number of years ago, almost a decade now, as we look forward, which we tend to do in IBM Research over a decade, that it wasn't going to be so much about doing the calculation. The fact that the data was going to explode. Now, it's exploded beyond even our wildest expectations. But it was going to be all about data. And as we look forward now, we're talking about the creation of as much data as the entire universe of stars. 10 to the 23rd, 10 to the 25th, it doesn't matter, it's a big number. And the von Neumann computer systems of the second programmable era will be almost useless in that truly big data space.
And why is that? Is it just the speed is just not keeping up with the torrent of data that's coming?
The speed, and we can go into, Moore's law has slowed, so the ability to calculate and keep up with the rate of data growth is no longer there. The energy it takes to move large amounts of data, even within a machine, much less continent to continent doing a business transaction, is impossible. The heat dissipation is tremendous. And I think even more fundamentally, it's not about doing a calculation on that data to get an answer. It's about exploring that data. It's about finding new correlations, new context in that data to provide new solutions. That's an entirely different thing than doing a set of calculations on something that you program. And so we set out to build an entirely different sort of computer. We refer to it as a cognitive system or cognitive era of computing because in a sense it mimics some aspects of what the human brain does. It doesn't just calculate. Yes, it has a big, fast memory, but the system, you don't program the system learns. It trains the way, in a similar fashion as a human being. It can reason. It has some perception about the environment that it's in. And so as you start to understand more about what Watson is, Watson is really the first computer in that new era of computing. So, as we have the stage here for Watson, it's a very important bookmark in the history of computing. In my mind, it's sort of a past reflection on what the previous era of computing was about, but first and foremost, it's a look forward in terms of what's coming over the next decades.
Let's talk about how Watson works. I think this is a great place to get into that, because we were down there for an hour tonight with people standing in the Jeopardy podium and looking at the touch screen, and they all had that question on their minds. How does Watson work?
Right. So, von Neumann architectures, we talked about how they do calculations. Search engines, keyword search, very, very simple lookups. Here's all possible places that keywords. It's a little bit more sophisticated, but it's keyword searches. Do a search, get 100 pages back. Watson does not do that. Watson first will ingest raw information in unstructured text. It's a very sophisticated natural language system, has incredible natural language capability built on 20 plus years of IBM research. So it can understand very subtle implications in natural language. It can draw correlations in context within different pieces of natural language information, number one. Number two is, I think the best way to think about Watson is it's a collective system or platform of multiple statistical engines. It uses sophisticated mathematics and statistical engines to not only understand the language, but look for possible information that could be relevant to whatever you're looking for. And then it does very sophisticated ranking of statistical probabilities. And if you remember, actually in the show, Watson would give an answer, but there was a little answer bar in the bottom, and it would show the top 3 answers that Watson was considering. And Watson knew what it knew, and it knew what it didn't know. It had a probability associated with every answer. So it wasn't like getting 100 pages of search. It's rank ordered, statistically, probabilistically answers. Watson also had learning engines, and has learning engines, which are very sophisticated. So not only does it do these calculations at a point in time, but it learns from what it gets right and what it gets wrong, or who it's competing against. So it's a very sophisticated set of mathematical statistical engines, which, as I mentioned before, once base programmed, the programming is never touched again. You can add algorithms, but what Watson wants is information and data and examples of what's right and what's wrong, and it wants to learn who can I trust and what information can I trust, and then it will start to statistically rank that higher. So entirely different kind of system, statistically oriented because it's dealing with uncertain data.
How many people and how long did it take to work at that base level of programming that you're talking about, which was the foundation that allowed you to say, now we've reached the tipping point, now it's really working?
We had a team come up with, in 2 or 3 years, this approach of sort of open statistical analysis. That said, when we first applied this to the simple Jeopardy question set, we were about 3 years before the winning game. And Watson, on the systems of that day with the algorithms we had, its precision or probability of being right was about 30 or 40%, and it would take an hour to an hour and a half to come up with an answer. That does not make for a good game show, much less a good advisor for a medical doctor. But yet we could see the progress of that system. And it was over the next 3.5 years that we went from 30 to 40% probability in an hour and a half to what we called the winner's circle to compete with a Rudder and Jennings, where we had to be 85 to 90% correct and precise. And we had to answer that and do all of the searches and algorithms within about 2.5 seconds. Roughly speaking, although we were running things in parallel, we had a second to understand the question in complex natural language. We had about a second to find all possibilities. We had about a half a second to decide what we knew, what we didn't know, and were we going to bet or not. And
That's
so
tough.
how much. in about 500 milliseconds. That is a really tough problem. And to this day, no one else in the industry, to my knowledge, has accomplished that.
As tough as that is, on top of it, you really sort of bet the farm when you decide you're going to go on television and play Jeopardy.
Oh, yes.
So of all the things that you could have decided to do to develop
Yes.
Watson and prove out that technology, why play Jeopardy?
It was, first of all, in the research and development of the system, it was a great way to test our progress. Again, open domain questioning, and there was a corpus of previous games. So we could test our progress against that system, which in core research may not be so important, but as we wanted to progress, through development and commercialization of this, we had to know that we were moving in the right direction. We had to know that as we plugged in 2 new statistical algorithms, the system got better and not worse. Otherwise, we'd be fumbling around for 20 years versus, 3 years. And so it became a great test bed for us. And then it was, I remember the gut check was 1 year before the taping of the show. We had to sign the contract with Sony.
And were they enthusiastic about this, by the way? Did they think this was a good idea, or did you
Well,
have to
honestly,
talk them into it?
honestly, at first, they really questioned our sanity. They questioned, was this some sort of trick or parlor trick? And they made multiple trips to Yorktown to see the system in action over the course of a couple of years, to the point where they were convinced that this is the real deal and something really special is happening. And they made the flip to, we want to become part of history. But we had to sign the contract a year before, and at the time it was taking us many minutes to answer a question. But
Minutes,
but versus 2.5 seconds. But we decided to sign up and in our culture, put the IBM brand on national television. And we worked pretty hard for a year.
Now, we're barely 2 years on since that Jeopardy match, and yet so much has happened in the evolution of that system. Can you talk for a minute before we get to questions from the audience about the vision for Watson as it stands now and how it's being deployed against that vision?
Yes. So we decided actually before we won the tournament that it was going to be just as the Deep Blue Chess Championship was won. We were going to do that, win or lose. We were going to move on to doing important things with the system. And as we thought about what to do, we narrowed down to 2 or 3 different industries that we wanted to put Watson into, where we felt we could make a difference. And again, sort of being grand challenge guys, Coco genome, whatever, we said, okay, where is there big data, where is there noisy data, and where can we have the largest impact on society, and also obviously on the IBM company. And so we said healthcare, and we said, okay, where are the biggest problems in healthcare? Some of the biggest problems are in cancer. And so we decided to go after that field with Watson, and Watson has spent fundamentally the last 2 years working with the top oncologists and medical institutions in the United States in doing cancer research and developing cancer protocols and assisting doctors and nurses in diagnosis. But fundamentally, we have not been reprogramming Watson for the past 2 years. Watson has been learning all of the world's knowledge, written knowledge, about cancer research, and Watson has been studying and analyzing all of the records in places like Memorial Sloan Kettering, MD Anderson Cleveland Clinic, and basically learning what's right and what's wrong, and actually learning the language or the dialect of medicine. And so Watson is now being deployed in some big insurance companies like WellPoint, and Watson is literally in medical school at Cleveland Clinic, and Watson is working with a couple of dozen of the world's top oncologists at Memorial Sloan Kettering.
And how is the field responding to this?
Outstanding. It's very interesting. We thought at first, I shouldn't be picking on medical doctors, but medical doctors, rightfully so, have been reluctant to adopt information technology in the past. What we experienced with Watson was it was such a leap forward, and it ripped them so far out of their comfort zone. It wasn't just a new pad or something they had to enter medical records in. They saw it as a way of advancing their own capability and deploying their knowledge. And so the reaction we got around Watson was just incredible.
You know, a couple of people have said here at the museum, as we've talked about this whole era of bigger, faster, smarter computers, they always in the back of their minds, there's something that kind of brings to mind the HAL 9000. And that moment when that true sort of sentient computer says, I'm sorry, Hal, I can't open the pod bay doors. Where do you fit Watson and the implications for the future in that scenario?
Well, first of all, we always know where the plug is. We can pull the plug.
Yeah, right, yeah.
I'm just kidding. No, look, Watson, we are always putting Watson in a situation where it's informing human beings and where the final decision will be the medical doctor, will be the practitioner in the field. Watson is not a decision. Watson does not make decisions. Watson is capable of analyzing information and presenting the results of vast amounts of information and analysis to a human to make a decision. We should talk about where Watson's going because there's some interesting interactions that go on between humans and Watson that we've observed in some of these fields. But it's all about informing people. And what we're finding, whether, again, it's in healthcare or the financial industry, that experts in their field use Watson not to get the top answer, number 1 or 2 diagnosis. They want to understand, well, what's number 3 and number 4 that Watson came up statistically? And they want to be able to probe into Watson's logic as to what sources did Watson use and how did Watson conclude that? Because that's where discovery occurs, and that's where they're making sure that their own, perhaps personal backgrounds and prejudices aren't influencing their decisions. So it's a very interesting, different kind of tool than a decision tool. It's a decision support tool, and it's a tool, in a sense, my analogy is, it's like a telescope looking at the physical universe. It's a telescope that's looking into and analyzing the digital universe that we're creating.
So this is a great question about you as a manager and how you manage. The word that's used here is egos of 3,000 scientists working around the world in 12 labs. What is that? What's your day like, John, when you take that on?
Well, so first of all, you don't manage. You do not manage researchers, at least not IBM researchers. This is the largest collection of wild ducks you ever want to meet. I cannot imagine even a subset of them flying in formation for any period of time. So it's my approach is very simple here. I've seen other large U.S. industrial research lab directors, people in my position say, you know what? Here's the right 20 things that we ought to be working on, and here's the only things we're going to be working on. If I were to say that, you should sell all your IBM stock if you want to. No individual is smart enough to know that. So I try to create an environment where it's okay to try these wild things. It's okay to do a Watson project. It's okay to fail because, as you know, we learn often more from failing than we do, and I think your museum is proof points around many of these things. And then the other thing I do, which is maybe the only important thing I do, is I can reallocate resources very fast. So in the case of Watson, when it was evident that Watson was beginning to learn, it was still taking a half an hour to answer a question, but we could see where it was going to go. I could say to that team, we're going to do this, and we're not going to fail, and whatever you need, you're going to get. And I remember that conversation with that team. They thought I was joking, and I said, no, however number of people, whoever you need, whatever amount of money you need, we're going to do it. And I think that's a great capability of a company like IBM and a scale of IBM that I don't have to run around to 15 companies, or I don't have to go out, I hope there's no VCs, I don't have to go out and ask for VC money. We could put whatever resource we needed on that to make that succeed. And so what I do is I create the environment, try to nurture the people, and then when I see success, I can move resources fast.
There's a question here about a world in which we have huge amounts of information, but knowledge and understanding seem to be sort of receding from us in some ways. And I wonder if you have a view about, in this world of big data and high-speed computing, are we going to see some sort of movement from information processing and retrieval to a point where we're really cultivating and deepening knowledge?
Yes. It's very clear to me from some of the most advanced work that we're doing on big data analytics that we truly are advancing knowledge. I sort of divide the world of big data and analytics into two pieces. One piece is, I'll call it Watson-like, which is a system and a capability that has the capability of learning and understanding all human knowledge that's been created. But in this world of big data, it's yet to be analyzed, it's yet to be understood. And so applying other techniques to search out correlations and context from that big data that's undiscovered, and then merging that with what a system like Watson can provide in terms of known human knowledge, I think is where the huge breakthroughs are going to occur. But this world of, again, overused term, but big data, there is tremendous knowledge in that if we could extract it. It's just too big, too uncertain for most systems to get at. And the human brain, just as we can't do the mathematical calculations of a supercomputer, we cannot get through that data. It's just too massive.
It also seems to me that what you've talked about tonight is really also systems that enable the application of human judgment to problems. It's aiding it, but the knowledge really seems to me to also come from the combination of Watson's capabilities and just human judgment and experience.
Yeah, we're starting to see some very interesting things occurring between the Watson system and humans that are interacting with it. We're seeing, I think perhaps for the first time, that obviously humans are learning from Watson in terms of the information that it's bringing forward. But we now have Watson capability that Watson can come back and say, okay, I've analyzed this. I think it's these three things. If I'm a medical doctor, this is my diagnosis. But you know what, doctor or medical student or patient, if you could tell me these two things, do you have this pain, or doctor's note, does this mean that? Then my understanding of the problem will go from 70 or 80% to 99%. And so we're seeing now, for the first time, a Watson system coming back to humans and saying, do you know this? Because there's certain things that humans will always know that the machine will not be able to figure out, or not be able to figure out the human information. And so we're now starting to see that it's not 1 + 1 = 2, but the rate of learning between the human and the system is greatly accelerated. And that is a brand new area of research for us in the human-machine interface.
So far, we haven't talked about the kind of hardware that this type of computing runs on.
Right.
Have you had to devise a certain kind of mechanical architectural platform that cognitive computing has to run on in order for it to really be successful?
Right. Yes. So, we've had to use the hardware and the tools that we have available. So, just as the first programmable systems were built with vacuum tubes from the previous era, the first Watson systems are built, with our silicon MOSFET switches. So it enabled the first capability. But as we look forward, it's very, very clear to us that between the slowing of Moore's law, even though there's many technologies to advance that, entirely new technologies are going to be required for this new era of computing. Just a very, very simple example. In a Watson system, the time and distance between, and cycles and latency, between data and memory and the processor is absolutely critical. Watson had no disk drives. In 2.5 seconds, with the size of the data we did not have the time to go outside the system. So all of Watson's knowledge was in memory. So extrapolate that now forward to these enormous databases. We have to move the memory and the data very close to the processing, as close as possible, and perhaps someday it will be a common switch or entity doing both. And so completely new types of devices.
So that's a whole new design.
Whole new design, whole new underlying technologies. And we've fundamentally, just as we had to replace the vacuum tube with silicon technology, we're going to have to replace current silicon technology with something else to have a 40 or 50-year run at this new era of computing.
So let's talk about the future now. There are a couple of things that I would like to ask you about, and then sort of get your kind of closing thought on where all of this is headed. There's something in particular that you're working on I wanted to talk about, which is the relationship between this kind of computing and the brain. I know IBM is doing a tremendous amount of brain research and has some models in mind and some destinations it would like to achieve. Can you talk a little bit about that particular part of your work?
Sure. So we believe that ultimately, as we go down the path of cognitive systems, that these systems will be bio-inspired in some manner, shape, or form.
That's the phrase you use, isn't it?
Yeah,
bio-inspired.
Bio-inspired. And it comes down to a very simple set of numbers. 20 watts, average human brain, a lot of people with more than 20 watts in this room. But, Watson, 85,000 watts, 85 kilowatts for the system required to beat two 20-watt light bulbs. Smart light bulbs, but light bulbs. Something's wrong. Something's wrong with the brute force that we're using to do that kind of calculation or that kind of big data statistical analysis. So we have to learn more about how the human brain works. We understand a lot. We're doing a lot of research. We've collected the world's history of mapping the human brain. We're working with some of the top brain researchers around the world in understanding how the brain works. It's extremely efficient. It's probably more analog than digital, separating, back to the von Neumann question, separating memory from processing, not so clear. The wiring diagram of the brain still being investigated. The state of the art in the world in mapping brains is a portion of a fruit fly's brain in terms of mapping the wiring diagram. And even when that's complete, we will not understand fundamentally how that fruit fly's brain really works. So, but that said, we can gain a lot of information in terms of how the brain works. And so we have projects, believe it or not, within IBM Research, working on that effort, working in partnership with great universities, medical institutions. We have work going on here at Ahmedin on a very large DARPA project called Synapse to build, again, using the best silicon technology, the lowest power silicon technology, building large arrays to mimic large masses of synapses and neurons, and starting to study alternate architectures that might be what's going on in our brains. But this is a journey. This is an era of computing. This isn't one computer system or two or three, in a line of PCs. We're talking a journey here of the next 40 or 50 years in cognitive computing. And so we need to understand now, what are the technologies that are going to be required 20, 30, 40 years from now for these systems?
And do you have a roadmap? I mean, clearly things are changing so rapidly. There is no roadmap for 40 years out. But what are the pointers that you're looking at when you look ahead?
Yeah, we have a roadmap that, of course, gets fuzzier as you go out. But we know over the next decade, we know what we can do in silicon. We know in the 10 to 15 to 20 years what we can do in other silicon-like materials, compound devices. Lots of research in alternate material structures of switching-like devices, carbon-based, nanotubes, graphene, et cetera. All sorts of combinations, huge research programs to take us over the next 10 or 20 years. But then the really exciting area is in completely different forms of memory devices. As you know, we've explored sort of the limits of memory. 12 atoms, 12 iron atoms on a surface is sort of the minimum to store a byte of information. So we're exploring, well, if we start from there and build up versus reduce down, how can we build completely different types of memory systems that will be not only tiny and fast, but can be co-located with logic devices. And then in terms of fast switches, the sort of the holy grail is quantum devices. And you know, we have a very large, one of the largest industrial quantum computing research efforts underway. And the progress over the last 4 or 5 years, John, has been very substantial. We've now built a couple of qubits, very high coherency, and we can now start to probe quantum behavior in computing. And with that, you know, we're not talking Moore's law anymore. We're not talking 10 or 20% or 2x or 10x. We're talking 10, 20, up to 40 orders of magnitude performance. Think of a Watson with 40 orders of magnitude compute power. That's a different deal.
Last question. Watson is obviously named for the great chairman and CEOs, Tom Watson Sr. and Tom Watson Jr. If Tom Watson Sr. came back today and he saw Watson and he saw these things that we were talking about, and he was viewing it from the world he knew in 1911 when he first went to CRT, or CTR rather, what do you think he would say? What do you think his reaction would be to the technology and the company that he would encounter today?
Well, I think first and foremost he would be proud. It's his company, was his company, is his company. You can tell the culture now coming out from IBM.
Yeah.
But he created this company, he created the culture of the company. He and his son created IBM Research and said, this is our strategy, this is our value proposition to the world. And he wasn't thinking to one client, he was thinking the world. You know, he was the first big multinational corporation in the world. In a sense, created much of the information technology industry. So I think first and foremost, he would be proud. I think he would be awestruck with what the system can do compared to the systems that he knew. You know, T.J. Watson, remember, he started the company on meat slicers and cheese slicers. That's a long ways from a cheese slicer to a Watson computer. But I think he would see in the system and the way it's being used the kinds of values that he created in the company, which is it's not just about building a computer, it's about doing something important for the world. In his day and age, it was, as your museum so effectively captures, it was about creating a system that could, you know, do a census of the United States or help the United States defense. So it was always about a big problem and solving a big problem, and then he knew the company would be successful. So I think he'd be very proud of what the company's achieved.
John, you've been very generous with your time tonight. We're so glad to have you here. It's been wonderful. Thanks very much.
Thank you, John.
Many observers believe the technology behind IBM's Watson will lead to a major future breakthrough in artificial intelligence. There are hundreds of stories like this at the Computer History Museum. Join us next time for the Computer History Museum presents Revolutionaries.